Good afternoon, good evening, and greetings, everyone. Thank you for joining this session on leveraging operational scenarios. And this is going to be very exciting couple of hours. And with me, I have JB, and I'm really pleased to have him for this session. And welcome. And so, JB, maybe we can start with your introduction.
Thanks, Mudit. No, and a really exciting opportunity here. Looking forward to this conversation in a sense. So my background, just very briefly, is been primarily in the aviation domain, and in that space, in defense aviation to start with, literally aircraft, and then into systems engineering for avionic systems, and then off into modeling and simulation. A large portion of my career of 30 plus years, about 20 flight and mission simulators in the defense context. So over that time, I really realized the value proposition of systems thinking, modeling, and simulation, and that's really my passion. In terms of qualifications, computer science and BSc in aerospace engineering, went on to do a master's in systems engineering sort of mid-career, and I'm currently enrolled in a PhD at the University of Adelaide with Scholl as the industry sponsor, so it's an industry-sponsored PhD. Australia chapter, CESA, the Systems Engineering Society of Australia. And back to you, Mudit. Thanks.
Right. Yeah, thank you, JB. So my name is Mudit, and I basically have about 14 years of industry experience. I started my career as a hardware developer. Been always mostly in the automotive electronics area. By education, I'm an electronics engineer, and then slowly I also did my MS in embedded systems. And then as I was working through it, I really started gaining interest in systems engineering and how systems work at large. Been involved in a lot of innovation projects and product development in embedded systems. So that's when I got introduced to systems engineering. And for last 7 or 8 years, I've been involved in systems engineering and model-based system engineering, essentially. Doing simulations as well as doing a lot of SysML-based modeling of both systems and worksite. And also about a few years back, I got my SDM certificate from Massachusetts, and that's where it sort of officially started the path or the career into systems engineering. I'm also the technology director for Blue Sky Solutions, and within COSE, I've been associated for many years now. I'm currently holding the post of president for INCOSE India chapter, and I'm co-chairing the INCOSE India MBSE local working group. So that will be my introduction. Next slide, please. Yeah, so we actually welcome you again from Blue Sky, and we'd like to quickly introduce our company and the services we offer. So we are basically a systems engineering consulting organization. We strongly believe in digital engineering. And we are here to support any organization who would like to adopt the digital engineering practices, going from supporting them to go from the document-based to digital engineering, model-based engineering efforts. And what we offer is services in terms of analysis, such as you want to increase the operational efficiency of any program or your project, develop a roadmap, or adopt system engineering processes. You want to tailor them according to your PDP. So all that, along with consulting and project execution in terms of system engineering effort, model-based systems engineering, modeling, simulation, and a lot of competency development through workshops and trainings. We've been working with different industry verticals like automotive, off-highway, aerospace, and defense and industries. And we are really happy that we have a great team with collective years of onboard experience of about 70 years in system engineering. And we have certifications from various prestigious institutes such as MIT, Caltech, and so. So yeah, thank you, JB. Maybe over to you now.
Thanks, Udit. So I'll do a very quick, well, you've done the personal introduction, that just sort of expand on that. So really my passion right at the moment going forward, building on my career, is on really advocating for evangelizing, the power of these concepts of systems thinking, modeling, and simulation as being foundational to helping us understand the world we live in, to break down complexity, and to create the reality that we so desire. And systems engineering is that set of competencies and that role that brings these foundational competencies together and enables the translation of these concepts into tangible capabilities in the most efficient and effective manner. And if you look at what the role of the systems engineer is, it's absolutely fundamental, and that's what we do. And so, my passion now is to spread that word. And as I pointed out, just kicked off a PhD with Scholl in that space as the industry sponsor, and struggling at the moment to try and focus it, but that's the intent. So I might keep going then with it. Back to you.
Yeah. So yeah, and I'm just very pleased to share that we had over 100 plus registrations. This you can see the distribution of the industries that are participating in today's session. Right from automotive, aviation, software, defense, healthcare. We have a lot of people coming from different areas of expertise. And we also have people joining us from across the globe. So, I mean, it's heavily focused in India, but then we have a lot of people coming from Australia. We also have a few people coming in from Canada and the US. So the next slide, please. I would like to show that in detail. So this is a quick chart showing just the distribution of where the registrations are from and which verticals are there from. Yeah, that's about it. So I think we can go ahead. Oh yeah, very, very important. So we actually did a poll, and what we asked was that what were some of your go-to methods for eliciting system requirements? And the 100% turnout was actually stakeholder interviews. And that's very interesting because that really is the starting point. But what we are going to cover today will also touch upon how you could do use case analysis in ConOps and OpsCon to really go into delving further into understanding your system requirements. So it's going to be very interesting. Yeah. Next, please.
Okay, so let's get started. So to start this off, I found a very short little video that sort of goes back a bit in terms of the genesis almost of the application of systems thinking, modeling and simulation, and these concepts in an approach that really was intended to go a certain way, but ended up going a completely different way, but still had unintended but very positive consequences. But it sort of highlights where this thing, systems engineering and systems thinking, it came from, in one sense, in a direct application and defense construct. So I might do that to start with, and then we'll sort of move on from there. So let me know if the sound's coming through okay with it.
Yes.
Operational research began in the First World War when science was introduced in order to improve on military operations. In February 1917, German U-boats intensified their assault on Britain's Atlantic supply line, sinking 1 in 10 ships sailing every month. British scientists analysed all available data and created the best possible model of the convoy survival. Just 6 months later, losses were down.
Just wondering, sorry, I just got to say, if anyone is on, if you could just go on mute, please, would be appreciated. I think there could be a bit of sound issues there, but here we go, back again.
Down to a remarkable 1 in 200. Not only saving lives, but critically contributing to the survival of Great Britain. By 1934, analysts had identified a new problem. Simulations showed that in the event of war, German bombers could easily deliver a knockout blow. By 1938, this knockout blow could be delivered in just 24 hours. The British government asked a group of scientists to explore the feasibility of using radio waves to create a death ray which could shoot down or cook approaching bombers. Instead, scientists demonstrated how radio waves could detect and range aircraft, and radar was born. However, technology alone was not enough. Working in close partnership with RAF officers, the new team was able to combine scientific research with operational experience to create the greatest air defence system in the world. This groundbreaking approach was rapidly integrated to a network of both military and civilian defence assets. With operational research, it enabled the earliest possible detection and interception of enemy aircraft. By the Battle of Britain, radar had increased Fighter Command's defensive capability by a factor of 10, and operational research doubled this to a factor of 20. In 1948, the Operational Research Club was founded, which 5 years later became the Operational Research Society. After the war, the scientists and officers involved in this pioneering approach found jobs in government, manufacturing, banking, health services, business, transport, defence, sport, and well beyond, taking the knowledge and insight of operational research with them, where it has been solving problems and supporting decisions with science ever since.
Right. So I'm going to keep going from that. So that provided a bit of context in where systems thinking, modeling simulation in the context of it came from, and operational research was the term used and is still used. But it shows how we started off as bringing the disciplines together, and then they all sort of went apart again. And I think we're seeing a convergence again. And what was interesting there was the concept of unintended consequences. You start off doing something and you end up with something else potentially. And there have been a lot of other examples of those sort of unintended consequences, not as positive or sometimes not as negative, but that's strangely so. So I'll give you some more examples of these just to get the thinking happening. So there was a problem back in the 50s in Vietnam, in Hanoi. The number of rats, the population of rats was exploding. And so the authorities, thought, how are we going to deal with this? And what they offered was a reward. They offered a reward for rats to be killed, but to keep it clean, they suggested that, to provide proof that you had killed the rats, you had to bring in their tails, and they would pay a reward based on the number of tails that were brought in. And clearly, the rat population started to drop because people were quite excited to kill the rats, and things started to get better. But then after a while, we had the entrepreneurs starting to recognize that, there was money to be had here. So what they would do was cut the tails off the rats and release them back into the population to breed, so there'd be more rats. So the rewards claim went up dramatically. But what also happened was that as did the rat population, and so it actually became worse than it started off with. There was a similar event that happened in this instance of good intended unintended consequences. In India, for example, again, and during British rule of India, Delhi had an outbreak of cobras, too many snakes. And they decided on a very quick fix as well. They offered a reward for killed cobras. And as would be expected initially, the cobra population went down. Once again, people saw an opportunity over here to make money out of the thing, and they started breeding them and then releasing and then killing them to claim the reward. The authorities decided that this was a bit of a problem and too many people were claiming the reward, so the scheme got cancelled. And now we had people with lots of cobras, and what did they do? They released them back into the population. Again, good intentions, unintended consequences. And systems thinking really, explains why this happens. And why when we look at a problem and we just don't deal with it holistically, we ended up in situations that could actually make it worse. And if you think about society today, think about some of the things that are happening today that we sort of fall into a similar category. We provide quick fixes and we end up with unintended consequences. One example that I'm seeing more in the US in particular, we're seeing, for example, there were hospitals that were offered a bonus if they dealt with patients with COVID, for example, right? And we started to see the number of COVID patients being reported going up dramatically. And so you can see how things can be abused. And so if we think about systems thinking, and a very quick contextualization again before we get into the guts of what we're going to talk about. There are a number of definitions of it. I think Peter Senge provides probably one of the best sort of overview definitions of what it is. And he calls it a conceptual framework. It's a body of knowledge, a set of tools that have evolved over time. And they help us understand the situation through, make it clearer so that we can deal with the change in a more effective manner. So I've got a personal definition of what systems thinking is. It sort of builds on Peter Senge's, essentially a conceptual framework. And I sort of bring in these two concepts of efficiency and effectiveness. And I think it's both of them coming together. And that's the power of systems thinking. It's not just about effectiveness, but also about efficiency that really helps us break down the challenges we perceive and actually create the reality we desire. And I absolutely firmly believe that it's complemented by modeling and simulation. Now, that video show that we started off with was really building on both those concepts. But I think as we go through this, you'll start to hopefully see how these are absolutely fundamental building blocks to understanding the world and to engineering systems. But at the end of the day, what they help us do is answer these three key questions. And if you think about it, anything that we want to understand, as a minimum, we really want to answer these three key questions. And sometimes we sort of get stuck with just the what answer and don't even realize or actively look at the how and the why answer. But they're absolutely fundamental. All three need to be answered to be able to understand systems. And there is a classic metaphor for this, and that of the iceberg model. And if I'm sure a lot of you have seen this before, but it's probably the most powerful metaphor that I've come across that has consistently proved to be useful. Forces you to think about this, to actually go not just at the surface where you react to something and just focus on the what, as was done with the cobras, with the rats in Hanoi, for example, but to start to look at go below the surface, start to look at patterns of behavior so that we can anticipate what comes next. Or go even further below that to look at the architectures that are driving the behaviors, and then look at the design of the system and understand, how it's doing it. But at the fundamental level, it's really understanding the mental models that are driving the design and the behaviors and truly transform systems to what we want them to be, the answer to the question, why? And what's interesting is that if we have to make significant change and or come up with the design of a system that actually has value, it's really all about what's below the surface. And what's below the surface is all about models. It's about systems models, mental models. And so you start to see how we weave this concept of modeling into the systems thinking element. And it's inherently about models, and we'll show as we go through how it's also about simulation and how these all come together. So in our talk today, this is what we're going to cover. So we're going to start off with a quick overview of systems models, what they are, map that into systems engineering of how we engineer systems and how these models are fundamental to the engineering of systems. Then home in on the concept of operations and how it sits as a key pillar in that continuum and is absolutely fundamental in getting it right. We'll then have a very short breakout session for a bit of a discussion on these concepts. We'll then follow on with the second part where we'll look at a case study. We'll then look at developing use cases. And we'll follow that up with the second breakout session, where we'll then apply some of these concepts. We'll come back after both of these sessions. We'll have a quick recap where we'll get people to talk about what they came out with out of the breakout sessions. And then finally, we'll finish off with a bit of a summary of the key concepts and then an open forum discussion for those that want to hang around and have a bit of a chat about this. So that's the context or the structure of how we're going to go forward. So let's get started on the first of these. So starting off with systems models. And the idea here is the question is, how do we understand the system? And to use as an example, I want to use the human system as something that we want to understand. And keep in mind, we're also looking to the answer to those three questions, right? What, how, and why. But look, naturally, when you look at a system, how do you understand the system? And what's the first thing that comes to mind? Obviously, you think about it, but more than likely you'll get the word analysis come in. People will say, we analyze the system to understand it. And what does that mean? So when we say we analyze the system to understand it, but it really means we break it down into its parts. We look at the parts, we understand them individually, then we aggregate them into the whole, and we come up with an understanding of the system. Now, what the human system tells us very quickly, that the parts are interdependent. How the heart is behaving at a particular point in time is not an isolated fact. It depends on how the muscles are, what your activity is, what how much energy you have in your body, how your muscles and skeletal system interact together to give you the strength that you need to perform the task that you're doing, and how much oxygen, for example, you'll be able to get into your lungs to be able to give your blood to be able to flow around in your circulatory system. So the systems are fundamentally interdependent. And that is a method of understanding a system. And Russell Ackoff has a definition that uses this method, and that is that how do you define a system? Well, it's a whole that consists of interdependent parts, each of which can affect the behavior and the properties of the system. So how well it can do in a particular situation, how it performs, and the properties that it possesses in the human system, your heart rate, your temperature, and those sorts of things. But map that back to any system, you'll see what that means. And this method has become the predominant method of how we understand systems, the method of analysis. It's this three-step method. Take a system, break it down to its parts, understand the relationship between the parts, aggregate them together, and you have the system. So, and really this answers the how question. It looks into the system to understand its architecture, its organizational, its interdependence. And it also tells you to a sense what the system can do, but it doesn't tell you what the system is required to do. So, for example, this is all very well, but what the requirements on a system will be requires another method. And what's interesting is that if you look at the methods that we've come to understand, the scientific method, for example, determinism, they all inherently apply this method of analysis. You look at physics, for example, it's all about finding the smallest particle, right? You break everything down until you get to the smallest particle, and you understand that, and then by aggregating back upwards, you understand the world, so to speak. The standard model of physics is all about understanding particles. We have a definition currently within Incosia what system is, and it in a sense also leverages off this definition, recognizing the fact that a system is an arrangement of parts or elements that together, when they come together, there's something happens. There's a synergy that happens that displays a set of behaviors and meaning that the individual parts do not. And so these two methods or definitions tell us a lot about the composition of a system and of its part and how a system works, what it does, but they don't tell you what it should do. So to actually look at what the system should do, we need to answer the full what question. We need to look outside the system. We need to look into its environment. And there's a name for that. It's called synthesis. So in the human system, what the human must do depends on the environment that the human exists in. And that applies again to any system. And you can see, for example, the social context that humans exist in, family, your work aspect of it, your friends, the society, the cultural aspects. They're what drive the requirements on what you need to do in a particular context, in a particular environment. And so this is the context of operational interdependence. And again, everything is interdependent in an operational sense in the environment that the system exists. So we've got questions to the how and the what, and to some extent the why. And we have another definition again from Russell Ackoff that I like, is that a system then is a whole, that it's defined by the essential functions which it needs to perform within the larger systems of which it is a part. And we'll come back to this. So when you think of how do you define the requirements for a system, it's not about looking in, it's about looking out. It's understanding the operational context within the system, in which the systems exist. And hence the focus of this class too is on that operational context. So these two questions answer the how and the what, but really do they completely answer the why question? And well, do they? So if you look at these two, this image here, there's a dog, and we have these two children. And one is confident, petting the dog, interacting with the dog, where the other one's apprehensive and being away from the dog. Now, if you look at the how and the what, their structure and the environment they're in, probably very similar. But there's a difference over here in terms of how they're behaving. And if you try and understand that, what we find is Why is one seeing the dog as a friendly creature and the other one seeing it as something scary? And what's obvious over here is there's been an experience that has happened in the past that has caused one child to behave a certain way because of something that happened and the other not to. And so we have to really factor in this third perspective, this temporal, this time perspective into any system to understand the why question. We have to understand its heritage, where did it come from, and what its aspirations are. You can see from the child standing over here, she's really keen to actually engage, but is reluctant to because of the fear of some past experience. But the aspiration is to engage. And this brings into play that third dimension of understanding a system of genesis, that of its evolutionary interdependence and its aspirations. So to understand a system, we really need to answer these three questions. And to do that, we've got to come at it from these three perspectives. We have to look into the system to understand its structure. And the analysis method gives you that. It provides knowledge focused inside of how the system works and what the system does, but it doesn't answer the what question completely. To understand what the system does, you have to look outside the system, apply the method of synthesis, and this will tell you what the system should do by understanding the operational context within which the system exists. And then to answer the why question, really we have to look at the evolution of both of those aspects, the structure of the system and its environment over time and where it's going. And that gives us a third perspective, that the system is a whole whose behavior is a result of its evolving structure and its evolving environment. In other words, its heritage and its aspirations. And those need to be considered when we understand the why of a system. So it should, if you map it back to any type of system, I just use the human system as an example, that each of these perspectives apply. And to truly understand the system, we need to be looking at all of these perspectives to understand them and have suitable answers so that we can look at the interactions that exist within the system, outside the system, and from a temporal perspective, that happened in the past and that we look forward to in the future. When we think of a system, now from a systems engineering perspective, and we look inside the system, but truly to understand the system, there are a number of systems we need to think about. So the system itself, as we said, it has a boundary, and there are a number of names used for it. In defense, there's the context of the mission system. So for example, if you're designing an aircraft, that's the mission system, or a ship, or it could be a car, for example, which is the system of interest. And typically that system operates in an environment, and that environment has a number of different variables in it that then define the requirements on that system. And that environment also has other systems that it needs to interact with. So when we think of a system in that sense, we must think of not just the system itself, but of the environmental system that it interacts with. And there's some examples of those types of systems. And then there's a third category of system as well. There's the systems that enable the system to do what it has to do. And so if you look at that third category of system, we can further break that down. There's the system that will bring it into being in terms of the acquisition of it, and that will develop it. Just a second. And that is the system that brings it into being, and typically it's called the acquisition management system. Then there is a system that will sustain it through its life to continue to do what it needs to do. And we typically can break that down into three use cases. We want to be able to use the system, operate it to do what it's supposed to do. We have to maintain the system so it continues to do what it's supposed to do. And we might want to modify the system to make it do something different. And then at the end of its life, we take it out of service and we dispose of it. There is one last category of system that I want to highlight, and that's the systems that it inherits from. And again, in a literal technological sense, there'll be some technologies that will come in that will force the system that we are trying to design or build to have certain characteristics, to meet certain interfaces. And so we need to be cognizant of that. So when we think of a system from a systems engineering perspective, it's right about understanding the requirements of the system and the system it interacts with, but we have also to consider, very importantly, the management systems and the use cases that would apply to the management systems so that we actually will deliver a holistic system. So when we define the requirements, for example, of a system, it's not just about defining the requirements of the car or the aircraft or the whatever it might be, but also about all of the interfaces that it has with the systems it interacts with, and all of the enabling systems that will need to be put in place for it to do what it has to do. For example, of a car, you have to have a means to, from a use perspective, to be able to train people how to drive the car. You need to have maintenance approaches to be able to maintain it, and you might want to modify it to add parts in. And that philosophy then applies. So we have these four systems. The system of interest, which is the one that we're most primarily focused on. The interacting systems that it needs to interact with, and the interfaces and the drivers that provides. The enabling systems that enable the system to actually exist, and the influencing systems that come in that enforce or constrain the system in a sense. And that provides a framework that we then can use to define a holistic set of requirements when we want to define the capability as a whole, and not just about the system of interest and the technology. So I want to move in from there into the systems engineering, and we'll have time at the end to discuss in detail this is more a contextual approach of what systems engineering is, and most of you probably recognize this. So systems engineering typically is a process that goes from a need to a capability. We go through these phases: requirements, design, detail design, development, integration, and so on. Typically, we establish baselines along the way, and again, we'll come back to these if needed. For the purposes of this discussion, I want to stay at a very high level. And we have mandated system reviews that check each of these baselines as we progress through that system. We might use an incremental or an agile type approach, or we might use a waterfall or a staged approach. But inherently, whichever approach we use, this is what we're trying to do. We're trying to go from a need to a capability at the end of the day. And the focus is continually on a progressive realization of a physical system. So we think of that physical system at the end that we want to produce. And typically, when people ask you what is systems engineering, the standard answer you get, well, it's really just good engineering practice, following process to engineer systems. And there is a new definition that INCOSE put out recently, which I think is greatly improved. And it highlights the fact that systems engineering is this transdisciplinary and integrative approach. And it highlights the fact about it applying systems principles and concepts that allow for this process to be established and to happen. And we'll touch on some of these, and we'll come back again in detail when we need to, if we need to. My personal definition sort of builds on that, but it really talks about this aspect of here. It's the application of these systemic principles and concepts, and I'll explain these more in a minute, in a systematic whole-of-life framework that is the most efficient and effective way to transform a concept into a capability. And let me explain a bit more about that. So when we think about engineering a system, what really is our underlying intent? So we've got some real-world operational context, and we want to translate that into a tangible capability that does something. I've introduced two sort of streams over here, just to highlight them, not to go into detail. Again, we can go into detail if we need to. But there's a system definition stream, and then a realization stream, and then there's a verification and validation stream. And these go in parallel, and they progressively take us through this systems engineering life cycle. The requirements traceability matrix, that's what RTM stands for, facilitates that traceability all the way through to the end. And we have a physical configuration audit that checks that the system that is delivered actually matches the design and the specifications that were defined for it as we progress through these baselines. We have the VCRM, or standard term of a verification cross-reference matrix, that is the means that takes us through the verification stream to ensure that we build the system right and that we built the right system, and we use a functional configuration audit at the end that will check that we've actually done all of that. And collectively, the PCA and the FCA is our confirmation that we've built what we set out to build at the start. I am touching on this very briefly, and again, we'll come back in more discussion. For the purposes of this discussion, I just want to set the context. So at the end of the day, what we're trying to do is to translate a concept, create a solution in the most effective and efficient manner. And if you think about that, you've probably seen this, but at the heart of every capability, these words probably ring true, right? Everything is created twice, once in the mental plane and once in the physical plane. So someone has a thought or a concept that is of some value, and we engineer systems to translate that concept into a capability. So we're talking, what is a concept? A concept really is well, very simplistically speaking, is a model, right? It's a model of a system that's in someone's mind. And so we have a conceptual model of the system, and we want to translate that conceptual model into a tangible physical model of the system that's the real thing. So there we have the two models that these individuals over here are referencing. Everything created twice, once in the mind and one in the physical plane. Systems engineering, I think, actually creates four models. In fact, there's a lot more, but there's four fundamental models that we create through this construct. And these four models are fundamental to that engineering of systems as we go through them. This is a very quick and simple animation, again, not to go into detail, but to highlight the steps that we typically go through in this transition from a concept to a capability. So we have a concept, we have some needs, we translate that into a set of goals. We then translate that into use cases, and we will talk about these in a bit more detail subsequently. The use cases define a set of requirements. We architect those requirements into a functional architecture. We then map that into a physical architecture. We develop that physical architecture. We deliver the physical architecture, which is the capability. So in a sense, we essentially have these four models of the system. We have a conceptual model that starts off with in the user's heads. We have a functional model that we then extract out of their heads, which forms the basis of the engineering of the system. We translate that into the creation of a physical model through design. We implement that physical model, which then becomes the capability. And so we end up with these four models of the system, and the engineering of systems is the migration or the path that takes us in a progressive fashion, consistently, holistically, systemically, and systematically from this concept to a capability. And doing it appropriately will guarantee the match between that capability and the concept. And when we jump to the concept to the capability without understanding the concepts, that's where we run into problems. So what are we trying to do in this first phase? So in that first phase, the need assessment, the requirements definition phase, the purpose of that phase really is to capture that concept of that system of interest, is to extract the things that are in individuals' minds, the stakeholders, into a concept that we can all share and understand, and then to verify and validate that with the users to ensure that that concept is consistent and complete. And we'll go through a bit more detail into how we do that. I mentioned before, to understand the system, those three methods, genesis, analysis, and synthesis. And I think those are fundamental into understanding that. So we have to query the user to understand their understanding of what's in the system, what's the operational context that exists within, where is that thought coming from, and what are their aspirations of where they would like to take it. And that's what helps us do this. We typically review that at the system definition or system design review. Again, just for contextual purposes over here. We then translate that through design and development into a physical model. We ensure the integrity and traceability of that model with the functional model. And typically that's the purpose of a critical design review, is to establish the validity of the physical model of the system. Does it map back to the functional model of the system completely and consistently? And have we verified that? And is it suitable to actually build a system that we want to build in terms of we validate it for its suitability in that regard? We then implement the system, and over time, we might evolve that system, and we end up with essentially a system and a capability that's delivered. And our job is really to ensure that we have a complete, consistent, and correlated model all the way through from concept to capability. And so if you want to look at the essence of what systems engineering or the engineering of systems is all about, it's where this blue line is. It's about establishing the concept, mapping that into an architecture and a design, and then translating that design into reality. But what we're interested in is the concept of operations. It's really this first bit over here. And this opportune moment for me to now hand back to Mudit to sort of continue the discussion for this. And Mudit, did you want to start sharing the screen, and I'll stop? And
no, we can continue from here.
Okay.
Right. Yeah. Thank you, JB. Thanks for setting that context. So basically, what we would like to go deep into now is the concept of operation. And just like JB shared, that this really is understanding how a system is going to get operated within its environment and what are the enabling systems. An important concept to understand the operation scenarios is called the concept of operation. And this really defines at a conceptual level how the system actually operates when it delivers value. So I think I really like this definition because it talks about delivering value as well. So you are looking at all the possible scenarios under which a system is going to work in or perform in while it is delivering a value to its stakeholders and users. Another definition over here is that it can also be defined not only for the system, but also for the service built upon the system. And we are going to actually look into an example now of how it can be built for both a system as well as the service built on top of it. So next slide, please. Yeah. And the idea here is that as you are going from understanding the problem domain, this concept of operation really helps you understand what really the problem is. Most often what happens is when we are developing systems, when we are designing systems, we tend to jump directly to the solution as engineers. And this is an idea to step back, think of what is it that is really required, what is the problem at hand, and understanding really how the system is going to get used. So really understanding the concept of operation helps you identify what are your stakeholders, who are your stakeholders, what are their needs, what does the business really wants from that system to achieve, what do the users really want from the system to achieve. And from there, you essentially identify your stakeholder requirements and go into your system requirements, which will help you design a better system that will actually that was actually wanted by the users. Yeah, and so this really helps you translate from problem space to the solution space. So next slide, please. So what you also want to share today is maybe a framework with you of how you can actually use concept of operation. In reality, there are several ways in which concept of operation could be captured. I've seen several big documents capturing a lot of things, like talking about the environment, talking about the system, talking how it is going to get operated, who are the various stakeholders. Here, what we have is a very simple example of an aircraft. Let's say a passenger aircraft that is going through the life cycle of one operation. So what you have is an aircraft that is about to embark passengers. So as you board the plane, you see that all of these things are happening in tandem around you. Once that is done, there's a pushback, then the taxi and the takeoff happens. When the takeoff happens, there's a climb, then you cruise up to an altitude. And after that, you basically start descending when you have reached your destination. As you approach the nearby airport, you start landing. There's a taxi beyond that, and then you reach at the parking gate, where you again start doing to disembark the passengers, unloading the cargo, and there are possibly another post-flight checks. This could be for the next flight or for even when the plane is going for a halt for the day. So what you see here is a nominal scenario. There could also happen is a non-nominal or off-nominal scenarios in which something can go wrong. So we are going to talk all about that, but this is a very good framework to think about a system in use. Right now, what I talked about was a system of interest was the aircraft itself. But let's say you are an aircraft carrier or an aircraft operator agency, and such as Indigo Airlines. You can build a service on top of that system and think of your operation in terms of concept of operations and how your operation should be architected. So with that, I think next slide, please. Yeah. I think that's covered. Yeah, please. Okay. So here's a very simple framework. And JB, I can request you to just maybe go next for a few times. So this is a very simple framework, which is get ready, get set, go, unset, and unready. And this is very analogous to a sprint, right? So when you run in a race, you really get on your mark, you are getting ready for it. Then you set, and then you start running. You do the sprint. Once that sprint is over, you start to slow down, and then you unready. So either you win, you lose, but you finish the race, and after that, that is the operation is over. So what we are going to do is we are going to use this framework today, and I'm going to explain to you how we are going to use it. But in the next slide, I'll give you one more example of how to use this framework. And you can essentially apply this framework on almost any operation, understanding any system in its life cycle. So next slide, please. So this is a very common example, which is not so common these days because of the COVID situation. But when you're going to work, going to office, what are the different things that you have to do or you have to do? So we can actually apply this framework right from your when you're getting ready to go to office till you have reached the office. So, and I would encourage people attendees to drop a message on the chat if they want, if they can identify any more things. So, for example, getting ready is brushing, bathing, cooking, packing. Your get set becomes you're packing the bag, you're packing your laptop, you're taking your car keys or your vehicle keys, you're locking the house, you have to take care of the kids. The go is really the operational part under which you're traveling either through a bus, you're driving, you're doing carpooling. There could be several things that can go in the go part. And then unset becomes your stopping and parking. And finally, unready is coming out of the vehicle and entering the building. Now, this is again is a nominal case. This happens. Now, in the next slide, what we are going to look at is what could go wrong in these scenarios. So, next slide, please. So, understanding once you have laid out your ConOps, you can actually find out what are your emergency situations, and then you can plan better for contingency. And if you want to plan for any risk mitigations. So, for example, when you're getting ready, there could be a power cut. You got up late. Maybe you're not feeling good today. While you are getting set, you are unable to find your keys. As you're traveling, during the travel itself, maybe the vehicle could break down. There's huge traffic in front of you. As you're coming out, you identify that the parking space is full. Now, what do we do? And sometimes that happens. It has happened with me. I have reached the office and I forgot to bring the ID card. Now I'm not able to get into the building. So these are various wrongs that can happen or various risks that you can identify once you have identified your operational scenarios. And then you can plan better and identify the requirements that your system should satisfy so that it is working well. So with that, what we are going to do now is we are going to now break out into teams, and we will be giving you this framework. And I would, so Stuti here, she will be dropping you out into different small teams. And we will be sharing you links for your exercise workbook. So there's going to be an exercise workbook, which is live. So it's a live document. You can open that. And we will be taking about 7 minutes of a breakout session. And what you have to do is you have to think of a deploy and delivery drone. So just like Amazon and other companies are coming up with the application of a drone for delivery of goods, imagine that a delivery from a warehouse to someone's house is going to happen. What would the ConOps be for that? And you can use the same framework. Also, please be aware that we are using Teams right now. So it might take 10 seconds or so for you to fall into your subgroups. And please do, if you're done in your breakout room, please do not hit the leave button as you would drop off out of the call. So just wait, and we will get back to you into the main meeting room. With that, I think we can now split into different breakout rooms.
Sure, Madhut. Shall I paste the links here for the exercise workbook?
Yes, I think we can do that, and maybe also into the breakout rooms.
Okay.
Yeah, so every team has a separate link. So in whatever team you get allocated to, please choose the same team. Okay. Team number.
Just initiating the breakout rooms.
Sure. Thank you.
So if you and JB also get allotted, just come back out, I guess.
Yeah, sure.
Okay, I'm going to open up. So if you have don't have access to link, just message us. I will come into the breakout room and give you the links.
Yeah, thanks, Sudhi. Yeah, hello everyone. I think you can get started with the discussion. I've just requested Stuti to paste those links again. So this is room 4. So this is team 4. So please, you can. I've pasted the link. Please have a look at the link, and maybe you can just one person nominate to sort of drive it, and have the discussion started. I'll be dropping off from this meeting, and we will be back in around 5 minutes from now. 5-7 minutes from now, you'll get a message. Okay.
Cool.
Hey, Swati, thank you. Yeah, please go ahead, and maybe you can share screen as well if you want to drive this discussion.
I don't mind. Do I start? Do I drive the session or something?
Yeah, please go ahead.
Do we fill in the slides or?
Yeah, you can directly fill into the slides. So for the exercise 1, I think it's slide 6 or so. I don't remember exactly. And then there's an empty framework that you can do. All of you can feel free to edit that live. Yeah, if anyone can share the screen, that will also be great. That's also fine. Like you can utilize screen sharing, discuss.
I don't know. My screen share isn't working. Can someone else do it?
Okay.
Okay, I'm sharing the screen.
Okay, cool.
Okay, someone else is sharing?
Yeah.
Okay, no problem.
Okay.
Is it slide 6?
Yeah, it's slide 6. This one.
Okay, yeah.
So what would be the main steps? I think you begin with I think from warehouse to the person. So I think first you get the order, getting the order.
Plant. I think first we get it from the plant.
Yeah, you get the order from the some representative or something in those lines. Order. Check in the inventory whether the order is there or no. I think that is also. I think it's in get ready only.
Checking the availability in the inventory.
Yeah.
What comes in get set? Can you go on 2 slides up?
Get set is like packaging. When we will start packing, those things will come in get set.
So getting the order is something in yeah, so
Loading
get
the
set,
order?
I think. Yeah, the loading of the order. And what else? Also since it's a drone, so maybe even
Transportation, checking the shipments where it is.
transportation checking and like, is everything all right? Yeah, yeah. Loading the order. What else can be there?
Maintenance, maybe?
Maintenance, won't it come as like something as like as a checking? So won't that come in the other one, the like the contingency planning? Won't it come in that? I'm not sure.
Well, I thought like routine maintenance, so like every amount of hours they check.
Yeah.
Sometimes order line is like, order line is we have low. So that is okay. And pre-flights checks.
Hello, am I audible?
Checking also in the get
Yeah.
set, we can check like who will be the person. We assigning the delivery that who
Yeah.
will deliver.
Assigning employee or something.
Determining the flight.
It's automatic, right? Because it's a
Automatic,
drone.
but I'm pretty sure like there is, like so that we can get more number of orders done in one flight. I think that would make sense.
So it's auto, right?
Um, what else? Yeah, assigning
Delivery
orders. No, assigning like employees or something. Yeah.
Yep, this is
Yeah. Go get unset. Go. What else would come in go?
get unset like slow order line sometimes.
Determining path home. Like maybe the remaining, like removing the packaging, like last. I'm pretty sure there's some amount like unloading of the maybe unloading, loading, post flight checks.
Quality issues in
Yeah,
some of the product.
won't that be in get set though? Okay, no. It can be in get unset too.
Get unready. Yeah, get unready is someone is exchanging, returning the order because of the quality issues.
Why would we dismantle the battery?
No, for charging.
Okay, that way. Right. I think even post-flight checks come and get unset, maybe.
What? The mic cut off. Sorry.
Post-flight checks.
Post-flight checks. Okay. In
Yeah.
which one?
I think get unset. Right. That's me. Else can come in.
I don't know.
Yeah, that works. That works. Else is in go. It's just traveling, right? Like, so what else nothing else can come? Yes. We even add something like COVID checks or something like that as like get unchecked.
I mean,
Okay,
check the right delivery. Won't that be one of the post delivery?
Yes.
Um,
Closing is still in the process, so
sure. Actually, I had some issue with my system, so we'll be able to join that in just a few seconds.
no problem. I think it's also taking few seconds to close all the rooms. So
Okay. Yeah, people are coming back, I guess.
is my win?
yeah.
Is it still sharing my screen or?
No, there's no screen shared at this moment
Okay, good.
because the breakout rooms are closed. So we're all in the main room.
Okay, maybe Udit, you want to share your screen now and go from there, and then I'll come back after the next one, after the next break.
Yes, JB. So it's taking just a few more seconds from my side. So just give me a couple of more seconds, maybe 10 seconds. Sorry, I'm turning. So maybe what we can ask is, can maybe breakout room 1 or 2, any breakout room, would you like to share your findings? Maybe we can take a couple of breakout rooms.
So we had a pretty productive breakout room. So as someone from what was our breakout? Was it 2? Someone wants to talk about that? Just to put that, we can put the slide up.
Yeah. So do you want me to share team 2 slides?
I'm volunteering someone to talk.
Okay. Sure.
Yeah, but is anyone interested from?
I can share slide team 3 slides.
Excellent.
Yeah.
Let's do that.
Cool. All right, everyone can see my screen?
Yes.
Cool. I'll just remove it here. So first of all, we had the assumption that drone can carry multiple packages at the same time, and develop the use case for it. So get ready. We have to identify the right packages to be delivered, enter the destinations in the system, planning all the trips, like what would be the most efficient way. Then making sure drone has enough battery. If not, it needs to be charged. Then getting set would be picking up the packages, powering on and taking off. Go would be travel to destination, deliver the packages. Unset would be confirm the delivery of all the packages and return. Get unready would be power off and charge the battery.
Okay, great.
Yep.
I think that's really good. You have few marked in red and few in black. Any reason, or it's just
it's just the formatting of this slide anyway. Like I didn't change
okay.
it. It was already like that before.
Sure.
Yeah.
That's good. Okay. Yeah. Thank you. Anyone else would like to present? Maybe just one more breakout room.
Yeah, and while someone is thinking, I want to point out, I think one of in our breakout room too, there was a very good question that came up. I remember who asked that question about the difference between get ready and get set and get unset and get unready.
Yeah, I saw it on the chat.
And so we had a quick talk about that, and the suggestion that I sort of put forward, and really I think it's subjective, but was that once you go, the get ready one is not time constrained, but once you get into the get set, go, and the get unset, there are time constraints that you have to go along with in the main that separate the two out. So you can get ready in any time prior to the stuff, but once you get to the get set, then it's almost like the clock starts at that point in time. and you're going. So if you have to draw a line between the get ready and get set, that's one abstraction, not necessarily the only one, but that's one way of sort of separating the two things out.
Sure. No, that's really good, JB. I think. Yeah, I have not thought it that way, but it makes sense.
So let's see who else wants to. Let's have someone else share some of the stuff that they did.
Okay. If not, we can actually get going. We have only limited time.
Yeah, sorry, there's some in the chat link to PowerPoint link.
So I'll share my screen now.
Maybe if you have it, put it, and then you can continue with the presentation after that, right? So.
Yeah, I think we can drop that link into the chat, no problem.
I'll do that.
Yeah, thank you, Stuti. Okay, so, oops, got started from the beginning. Okay, so as you might have encountered some of these discussions, I just want to quickly recap what are the benefits of doing this exercise. Now, that was only one framework, and that was just 5 minutes given to you. But really, doing detailed ConOps can take good amount of time and good amount of experienced people giving their thoughts. Some of the benefits that are talked about in literature, and even we have felt personally, is that it really talks about the success on the left side of the V. It becomes a starting point of doing that analysis, starting that systems engineering journey. You're able to identify the right stakeholders, and it enables the communication between those stakeholders. So because you know what you have to talk to the other person. It gives you a high-level system definition, communication, and share the organization intents, elicit requirements from various stakeholders, and then requirements and designs that are aligned with user needs. So really what you're doing here is identifying how are you going to validate your system very early on, because you would now know is what are the real environmental conditions and constraints. So just like the team two that shared their ConOps, since they already identified what are the factors that need to be taken care in the get ready and get set stage, they can identify the right stakeholders in the design process, and they can have effective communication early on. They can also identify the right requirements that are going to be validated and verified once you have designed your system. So quickly moving on, I would like to introduce an example case study. And this is a work in progress. It's a work in progress by the INCOSE India MBSE working group. And we also have few participants from the working group onto the call today. So I'm really happy about that. So what we did is we started a MBSE challenge about 3 months back, wherein we were given a problem statement to build a case study, an MBSE case study for a braking system for a small passenger aircraft. And this problem is really in an open space. So it's more of a case study rather than doing the actual work. But what it really led to was that there were more than 60 registrations for this activity. We have about 25 to 30 active people who are working on it from across the industry. And only a handful of them are from aerospace. So even the non-aerospace guys are learning a lot about the aerospace. And what I want to talk about is really how we approach that problem and how it fits into this framework. So the problem was that you have to look at the braking system, and especially the brakes that go onto the wheels, which are a part of the landing gear, and focus on that. But really, to approach this problem, what we need to understand, as JB mentioned earlier, you have to think about the enabling system, identify your operational environment, identify the interacting systems along with, and of course, you need to begin with some kind of a purpose in mind. So the questions that we had is, what aircraft is it going to be designed for? So we sort of chose a sample aircraft, which was similar to what were the requirements given to us. How is it going to be used? What are those scenarios? What are those emergency conditions? Who's going to maintain it and when? What are the measures of effectiveness? What are your constraints? And then what are the environmental factors that will define some design constraints around it? So our approach became really understanding the high-level ConOps. And this is a snapshot from the same. This is our site on the bottom. So all of this work is actually a joint effort by the whole group of MBSE enthusiasts. So over here on the left, what we have is that the aircraft is probably at the hangar, and it is either in a maintenance state or an idle park state. And as it goes through its life cycle of operation, all of these are captured along with some decision boxes of emergency or non-normal or off-nominal conditions. So what I'll do is I will try to show it to you with the help of an animation so that it makes more sense. So, so over here, this is considering a nominal scenario. Let's say your aircraft is parked at the hangar. There is an initiate flight. It has reached the gate for the boarding. There are different activities that are happening. There could happen is an emergency situation right at the boarding, but we are not having that. It's a nominal condition. You're ready to take off. You've taken the takeoff. Then it's a normal takeoff. Even when you are doing a normal takeoff, it might happen that you have gained the full speed, and then there has been some medical emergency or some other emergency, and you had to reject the takeoff. Now, when you're rejecting that takeoff, that is actually the most dangerous part, because you are at your maximum weight of the aircraft, you are at the maximum speed of your aircraft on ground speed, and you have to brake. So really the brakes take the most heat, the most force, and most beating. And it might happen that the braking system might break. There could be burning of tires or accident. So it is a very dangerous situation. And therefore, that becomes sort of the extreme condition under which you have to design your system for. Now, considering that this was good, sorry, I accidentally, I think, moved forward. So let's say you're done with all that. You have the normal landing, and you have come back at the gate, and you're taxiing back to hangar and getting post-flight checked. Now, this is all done. What happens if there is an off-nominal scenario? Now, this is a very simple example right in the start that I've taken is, let's say everything is getting checked, but you are at the gate, and then suddenly there was an emergency situation and you had to come back, right? So that is one of the off-nominal scenario. So this is here what we have done is we have used a state machine diagram to depict the ConOps. But what you can see here is that there are several states here that are linked to special use case or special context under which the braking system has to go through. Okay. So I'll just move forward. What we started doing then is from there on, we started developing certain use cases for various contexts. So like in the previous diagram, there were situations in which the aircraft was either taxiing or was sort of taking off or landing, so or getting checked. So those are various scenarios. And under those scenarios and context, there could be several use cases. So for example, during the taxiing, the braking system is used to either slow down or even for turning around. When you are landing, it's all about land and halt. And whereas a secondary use case, which is more from the maintenance point of view, is the pre-flight checking. All of these use cases will help you identify further and better requirements for your system, will help you define your MOEs and your sort of the design envelope to come up with a good architecture that meets your requirement. And then, so essentially what I'm going to introduce to you is the topic of use case. And the use cases basically originate from a user's perspective. So whereas the ConOps that we studied before was coming at from the operational perspective or from a mission perspective. How is a user going to use the system in a specific scenario becomes a use case. And its focus is solely on the system and not on the mission. So I could turn around in any mission, but turning around is important and required, right? It might happen in a mission that turning is not even required. Okay, so that's the difference between the ConOps and the use case. And then each use case can be described using a behavioral diagram or a description. And in fact, you can use the same framework that we discussed just a few minutes back when we were doing the breakout session 1 to detail out a use case as well. So quickly, what we are going to do is we are going to go into another breakout session. And there, what you need to do is to identify the users and the use cases for a subsystem. And so this is the delivery drone. And what we are going to do is we are going to look at its subsystems. So here's a quick breakdown of a drone delivery system. It could be different architecture. This is just one of it, not a very detailed one. But what we want you to do is we want you to focus on only a few subsystems and think of the framework that you applied. Think of why a use case is important and how to detail out a use case, and develop use case for two subsystems. So maybe team one and team two will be working on vision system, and then team 3 and team 4 will be working on just the load carrying system. So assume what a load carrying subsystem would be under the drone, and assume what a vision system would be, and then who are the users for that, and how would they use it, and maybe you can use the same framework to detail out one of the use case. So yeah, and with that, I think it's time for another breakout. It was a very quick one, but let's break out into the same. It will be again a mix of teams, so it might happen that you get pushed to another team now. But please feel free to mingle together and work it out. So over to you, Stuti. From that,
Yeah, I'll just initiate that. It's the same link you have to use.
right.
I will repost those links for your reference once the breakout is completed. And the slides that Mudit has shown is there in in that link, so
Correct.
you will have a reference.
Yeah, and you also have a template slide to fill out the use cases. So I guess the last two slides in the slide deck. Okay, looks like we have the same team, so that's not too bad.
Yep.
Cool.
Load carrying system. Um, slide someone share?
Was it the same PowerPoint?
Yes.
Which slide?
I think you have to go to maybe second last or the last one. So I think slide 2 talks about which slide to go to. So you can just share. I can help you with that. Yes. So you have to work on slide 9 and 10. So maybe you can use the first column to identify who are your stakeholders, particularly for that subsystem. And then you can write their use cases into the rows.
Okay.
Mhm.
The different stakeholders for a load carrying system. I think the first one will be the gentle people who are going to take care of it. So the maintain. I don't think that's the name, but okay, sure. Um, um, the people who I think other stakeholders would also be the people who are already in the operations kind of thing, that like the people who have taken the orders and you're supposed to like those people maybe.
Okay, yeah.
So the recipients.
Yeah.
Okay. Yeah, I would encourage others also to join, please, the conversation if possible.
Others could be the designer also. I mean, as a stakeholder. I think
Okay.
a designer would be another block. verification.
What was it for again? What was the project or something for?
It was a load carrying system.
Like a crane or something, or?
Yeah. So if you go back to slide 8, the last one on the right, the load carrying system. So whatever subsystem that helps attach, detach, carry that package, right? Or if you have several packages. So what is that system that is carrying those packages or several packages and is able to deliver it? So the drone is only the mechanism of that is sort of doing the transportation, but there is a subsystem to it that is sort of carrying that, right?
For the drone, okay, yeah.
Yeah, but the focus is only on the subsystem at this point.
Okay.
So maybe it's fine if you are able to identify only a few users, but what is a use case there? Like, how is the operator going to use that subsystem in this whole context that you identified earlier?
Maybe one could be for the operator maintainer would be like depending on the load of say like you can to have multiple packages in like say one drone. We have to check the load. So depending on the amount of load that can be carried, maybe that is one. Like they can see the amount of like packages which can be put in one go. So like I think that could be your use case.
Like the size and weight of the packages.
Right. Yeah. So depending on that, they can like also determine that okay, these many packages could go, I guess.
But why would they use the crane to do that? Like the subsystem?
No,
They'd already have the information before.
They would have the information before, but in what sense to collect those many packets to add on the crane in some sense? Like it has a dependency on the attachment. I guess.
Okay.
That makes sense.
Sudhir, if you're speaking, we cannot hear you.
No, I'm not speaking. I'm just listening now.
Okay. Sure. That was a clever way to engage you, Sudhir.
Noted.
Designer would determine the amount of load, kind of. I think that would be there. The specification or the in that sense, yeah. Um, okay. Okay.
I don't know. Is that too direct or?
Deliver packages. Okay. What are the stakeholders? I think there would be more. Customer with respect to yeah, the receiving packages, but like making it easy for the consumer to actually like get it. No, the person who would actually remove it from the load carrying thing. Yeah. So those specifications and iterations could be done in that sense.
So now let's say it's already been identified. We have another 4 minutes to go.
Okay.
Could you break down, let's say, receive package from because customer is the primary stakeholder here, right? That's the
right.
Customer is always the king. So
right.
You go to maybe slide 10 now and see how would that receive package could be visualized. What are the steps there without even having an understanding of the system? Or maybe you are able to identify from this that what are the different functionalities that will be required for the system. right? So assuming that the drone has reached the destination where the receiver is, from that point to sort of coming back, how would that sequence go, right? Can
Okay,
you
so
can you identify those stages? And
after delivery, basically.
no, not after delivery. How would the delivery happen? Because you identified the use case as delivery, right?
Right.
So how would it happen? Is it going to happen in the hands of the person? Is it going to happen on a ground somewhere? But then what all needs to be considered?
Okay.
Right.
Okay.
Right. Yeah, exactly.
Um, I think one of the things that could be, yeah, that is an interesting point. That like, if where is it supposed to like really land? Safe landing space, but how accurately it's like,
Notify the customer. Yeah.
Okay, yeah.
So yeah, this is an interesting one. Do you want to notify before, during, or after, or all of it?
Probably before, because you don't know if they're there or not. You might have to
Okay.
abort the delivery.
Okay, so you're sort of not just notifying, but taking permission from them in some sense,
Yeah, I think.
right? And then you're probably notifying as it is happening. Even okay, now dropped. Now I'm going back. Whatever. So
Yeah.
Yeah.
that's a very interesting one. Yeah.
Um,
Can we have like authenticate and then deliver? Go.
Would that be receive permission or would be a separate one?
I think it would be in the same block because it comes in the same.
Mhm.
You can write it just below that, I guess. The receive sign off part, I guess.
Anything else? Or
No, I think this is good.
Fly back.
We're almost at time. So
I think you can add the authentication thing
where?
in the get set part only. Um, yeah. I think is it the same as the third one? I'm not sure. But that seemed like an interesting point.
I mean, it could be a part of Go because whatever the order delivered by that, we have to authenticate it has reached to the right customer.
okay. So you had permission. Now there are two kinds of permission. One is from the user, right? The other permission could be from the government of that region, if I'm flying in the right zone or not, right?
Yeah.
So now you're able to identify a few more stakeholders.
I think government is also one.
Yeah, we can say like regulatory boards.
Okay.
I know that.
This was good.
Oh, there you go.
I like the
We got
discussion.
halfway through, buddy. It's all right. It's an exercise. So most of you guys are in Pune, are you? It's
Looks
all
like
Pune
it.
crowd.
Yeah, looks like it. For a change, actually. Otherwise, you would see a lot of people coming from Bangalore.
Okay. How is COVID situation in India right now?
It's getting managed, I would say.
Okay.
But again, it's out there. So okay. So team
Yeah,
would like to go ahead.
go ahead, Mudit. Although I guess a few need to come back from the breakout
Okay.
rooms, but you can start the discussion.
Sure. Yeah, I was actually in team 4 and we were having good discussions here. So if you want to present or if any other team would like to present, please go ahead. I think we have time to take two.
See the correct
I would really encourage people to share. I can call out names of people I know.
I think
So JB,
it's good to,
can
to
also
share
do
some thoughts. That's right. It'll be good to share some thoughts.
Yeah.
If no one else is presenting, team 3 again.
Okay. Awesome.
Oh, cool. Someone is presenting.
So yeah, this is team 4. Okay. Yes, please go ahead.
Yeah, so mainly the stakeholders we identified were the primary, like pilot and the operators. The government and regulatory were also important. Like it came later in the point that every kind of a drone or something has to be regulated by the government also that we can go in these areas and things like that. Designers for the attachment itself, like they can identify what sort of the requirements could be met, and those are one. And obviously the customers are the highest priority here. So the use cases what we came up with it were in the next slide, I think. Yeah, in this, basically the drones identifying the location of the final delivery, then the safe landing, and we try to put the thing as like notifying the customer every time, like say the drone actually moves or something. So the customer would be notified that okay, are we allowed to actually come to the place or something like that. That was one. We also looked into dropping and loading authentication, that is the correct customer has received the order or no. And then we again transmit order confirmation and yeah, safe and pre-flight check, I think. Yeah, those are like the main things what we thought about in the discussion.
Sure. Yeah, thank you, Swati. Just want to add few thoughts here that even though so this is actually detailing out that the dropping thing, and some of the use cases would be assigned to that subsystem, but I also see some of the subs. This also helped identify a few of the use cases which are for the enabling system, right? So, for example, identification of the landing space or notifying the customer. These are all the enabling systems that will help that subsystem to sort of perform its duty. So, yeah, cool. I think we have time for one more team.
I'll share my screen.
Yes, yeah, maybe yes. Be good to hear from a couple more if possible.
Sure. So basically, stakeholders, we had too many stakeholders. We started with our subsystem was the vision subsystem. So the camera basically and recording of it. So the drone pilot was the obvious, then the customer, the quality manager of the delivery company, of the drone company, then the public and the nearby environment, civil aviation authority, the drone manufacturer, the parcel owner, like the Amazon in our case, any nearby airports, the camera supplier could be one of the stakeholder as well. Eventually, only use case we thought was the flight, delivery flight actually from takeoff, delivery, takeoff again, and then back to home base and land. And these are our basically some of the these are use case basically. So during the get ready phase, will be check and clean the camera, install the camera. Get set will be in making sure that you're receiving the correct feed. The go phase will be constant monitoring of that camera feed being delivered to the drone pilot. Get unset will be to detach the camera, and get unready will be to store the movie for later analysis, something along those lines.
Okay. Sure. Thank you.
Any feedback? Anything to add?
Thank you, Perry. Well done.
Yeah. Okay. Any other brave people out there who would like to share?
I think with all of these things, as we start to use the tool, people get more comfortable and familiar with it, and then it starts to fire, right? So, yeah, here we go. Well done.
Okay.
Hey guys, room 3 here.
Yeah.
So we were supposed to talk about the load carrying system, and we had like 3 different stakeholders in terms of the use cases, 3 different users. There's a seller, there's a buyer. Buyer is returning the product to seller, and there's a technician who is doing maintenance. These 2, seller and buyer, are similar use cases, and we already defined that in the previous breakout room. So we decided to go with the technician. So how does the technician interacts with the load carrying system? First of all, there's a department for the maintenance. They would check the schedule for the maintenance. So we are talking about proactive or preventative maintenance here. So they will check the schedule, plan all the tasks, check if the spare parts are available, assign the task to engineer or technician. Get set would be collecting all the parts necessary by the engineer. So these are the users, or actually users doing these activities, collecting all the tools and necessary parts, disengaging the load carrying system from the drone. Maintenance, then go would be maintenance tasks. So we have split it into 3 parts: cleaning, repair, replace. Getting unset would be put the load carrying system back, update the reports, fill out all the documents, approve the product for operation, pack up the tool and clean the workspace. That's again done by the engineer, and then the maintenance department actually puts it back in circulation. So yeah, that's pretty much it.
Okay.
Very well structured and very well presented. Thanks.
Yeah. Thanks for the addition. The framework, I'll probably use it.
Thank you.
Okay. Yeah. Thank you everyone for doing this. Maybe JB, would you like to share the screen and let's get.
How are we going for time, by the way? I've lost track. Yeah.
No, I think we are doing good. We are coming close to the end.
Okay, so I'm going to share screens. Where is the share screen? Here we go. So that was the last one, was it? So I'll just pass on. You keep going. There we go. Yeah.
Sure. Yeah. So coming back to this example of aircraft braking system, I cannot pull the whole information because we are still working, and it won't be wise to share everything that we have done. But it's just a snapshot of our work in progress. And based on that ConOps and the use case analysis that our teams have done, we have come up with several functional requirements. So just as you would have realized in your breakout teams, different teams were sort of had different views and different use cases that they were able to identify. And it was just in a matter of 5-10 minutes. But when you're working on it, you'll be able to identify what are those functionalities that are required from that subsystem, so that the overall objective of the mission is successful. So keeping that idea in mind, we were able to identify a few functional requirements, able to identify several safety requirements, and this is just a snapshot of that. So yeah, so this is maybe we can move to next slide, please.
Okay. Right. So now we're summarizing, right? So
yes.
Okay. So we're going to go through a quick summary of what we talked about, and then we just have an open discussion forum of any questions anyone might have. So just going through the top, we started off with systems models. and we looked at understanding systems. The three fundamental questions that we're looking to answer: the what, how, and the why. In order to do that, three perspectives: look inside the system to understand how it works in terms of its structure, architecture, organizational interdependence of the system internally. To understand what the system needs to do, look outside the system, method of synthesis. Look at the greater systems that the system is a part of, establish the interactions and relationships between those systems to define the requirements on the system in terms of what it needs to be able to do, and to understand why things are a certain way, the concept of Genesis, to look backwards and forwards in time, to look at the heritage and the aspirations, and to see how the structure of the system and its environment has evolved over time, and what the vision is for the future of what you would like the system to be, to then understand the system from a why perspective, why it exists, what its purpose is, and so on. And that method, to those three perspectives, to help us understand systems, or simple acronym GAS, and how that applies to pretty much any system. And then the second perspective there was also to recognize that while we're looking at a system, really we've got to look at the bigger picture here. And that bigger picture in this construct is all about the system within its environment, the systems that it interacts with in that environment, and its enabling systems that allow it to perform its purpose, that bring it into being, ensure that it can do what it has to do and take it out. And how the sustainment element, the enabling systems for sustainment, typically could be sort of further broken down into three use cases from a requirements perspective: in order to use or operate the system, in order to maintain the system, and in order to modify the system. So we took that then and we applied that into that framework, and then we moved on to the systems engineering context, again from a contextual perspective, and how the engineering of systems is all about the translation of a concept into a capability, and it's absolutely fundamental to get that to capture the concept as holistically as possible in order to get that translation right. We didn't go into detail about the actual systems engineering lifecycle in detail, but it was there for context, and that in itself is a matter of a complete course or a degree as far as you want to go into it. But that's the essence of what that systems engineering lifecycle is all about. And then we pretty much focused in on that concept capture phase, where Mudit then talked about how we sort of looked at that. And maybe Mudit, I'll hand over to you to probably continue the conversation over here. Just to recap.
Sure. So then we went into understanding some simple framework about ConOps and what is ConOps and how ConOps can really help you benefit to understand the problem space at large and identify the right system requirements to go deeper into the solution domain. And this was a good example about how service aircraft goes through its life cycle of operation. So maybe next slide, please. So we used a framework. I think we used it twice in the breakout session, and we also saw a very good addition by one of the teams. So I really enjoyed that. And we used this to identify the use cases, the sequence or the operational, the concept of operation for a drone delivery system. And after that, we went into understanding a case study, which was the INCOSA India chapter's MBSE working group case study. And through that, we looked another example of how you can define ConOps using a state machine diagram and how you can derive use cases out of it to understand what are your system level requirements. So, so you can go next, JB. We looked at what are use cases, some examples of the use cases, and what perspective a use case comes from. So essentially, it only comes from the perspective of a user. Its focus is on system and not on the mission. So in the first stage, you're trying to understand the overall mission. In the second stage, you're trying to understand focused from systems perspective. And to sort of go through this, we did another exercise using the similar framework to identify the users and the use cases and detail out one of them. And I think we are to a close now. So I think we can open it for feedback and discussions now. Any thoughts, any comments, any questions we still have plenty of time. And I think we had a question in the chat already, which was, can you differentiate between ConOps and OpsCon? I think this question came twice. So do you want to go ahead, JB? Maybe take the first shot.
Yes, so it's something that, because the terms are so similar, they get confused and misused and in a number of different contexts. But I mean, it's not a big deal. But if you have to look at semantics, one perspective, and this is not saying this is the law. When you say operational concept or OFCONs, the focus is on the system under development from a stakeholder perspective, right? So this is the operational concept for this particular stakeholder, and so it's the stakeholder's perspective on that. If you look at a concept of operations, it's looking at the system in its bigger context of what actually it does, how it operates in the environment in which it exists. So that's one view of separating the two, right? So operational concept, from a particular stakeholder perspective into the system. A concept of operations is the system within its environment operating, right? Doing everything that it's supposed to do. So an aircraft, it's from the point at which the aircraft comes out of the hangar, does everything and goes out. That would be the concept of operations of the aircraft. The OpCons might be from the perspective of a maintainer of the aircraft, right? What does the maintainer, how do they interact with that aircraft? And all of the use cases where I think Ish Bhutani really explained that really well, right? So you might have to do some preventative maintenance, you might do some corrective maintenance, you might make some temporary fixes, and those are the things that would be of relevance and the use cases that would apply for all the different parts and the different aspects that would be necessary to conduct those operations. Right, so it's the operational concept for a maintainer perspective. Does that help? And by the way, just feel free to turn your mics on and just talk. You don't have to type in the box, right? Does anyone disagree with that or have a different perspective on that? Because it's an absolutely open-ended thing that it just depends on which way you want to sort of frame it.
And then just to add it to that point, JB, even what I have seen is there are some standard templates that are often required in the acquisition and supply processes, really coming from the defense and the aerospace industry, wherein they require the ConOps in a certain format and they require the OpsCon or OCDs in a certain format, right? But essentially, the answer is it depends. That do what is right for that analysis or for that system.
Yes. Yeah.
So the way I differentiate between ConOps and OpsCon in military context is ConOps is what the Chief of Navy or Chief of Army or Chief of Air Force or the Prime Minister of India wants to achieve by that new capability. New class of submarine, new class of ship, new class of missiles, whatever that might be. Now, operational concept is how that particular piece of machinery will achieve its aim. That's how I differentiate. One is the leadership's intent of what the system needs to do and how it needs to achieve that capability. On the other end is a system level view of the system.
Yeah. And I think that's the fundamental point is whichever term you use, I think it's almost irrelevant, right? The fundamental point is there are two perspectives here. One is a stakeholder perspective, and the other one is an operational perspective, right? And maybe that's the way to perhaps look at it. Right. And as long as you cover those two, that helps you then develop a more complete understanding of the system, so you can scope it appropriately and then design it and build it appropriately.
Yeah. Agree, 100% agree.
Yeah.
Any other thoughts on that? And thanks, Barry. Thanks for jumping in there.
Yeah.
Anyone else got any thoughts on that topic or on any other points as well? I think just to add to Mudit's point, all of these things, these frameworks, these concepts, they are a means to an end, right? And it's a means. You use whatever means you think is the most appropriate and suited to what you're trying to do. it's an aid. It's an aid to help you do that. And I think this the framework, the get ready, get set, go, get unset, get unsteady. It's like a checklist in a sense. It helps you think of that, and you get better at it, and you know that by applying this you get a more complete picture, right? You don't miss things that inadvertently you would otherwise. It helps you fill that picture up.
Right, absolutely. So maybe I just wanted to understand from the audience here if they are doing such kind of analysis in their daily job, or they are facing any challenge. It's an open forum. We can actually discuss it out here. Would be great to know if you're using some alternate framework. So like this was just one of the frameworks that we thought we wanted to introduce in this conversation. But is there any other framework that you would like to share with the forum here?
Going a bit off topic from OpsCon and ConOps.
Sure.
Modit, you mentioned initially about modeling, like system modeling in terms of transitioning from a document-based systems engineering approach to a model-based approach, and typically a digital model. So I can see that's a very good, that's a very new transition in the industry. And just curious, I am aware about Capella. That's a tool that's available for that. Earlier, it used to be IBM Doors, which was used to kind of link up requirements, but it's not really possible to build system architecture in Doors. So it's still a document-based approach. So are there any other tools or stuff like that available that it's really new and under development? And I'm pretty sure a lot of that would be related to defense and military that are not open source, but are there any other open source products available?
Right. And maybe JB, you can add to it. So of course, Capella is probably the most commonly used open source tool. And they're following their own methodology and sort of semantics. What we have used in this presentation today was SysML, and we use a licensed tool called Cameo Systems Modeler. But if you are going towards SysML, which is sort of becoming now the de facto sort of language to represent architecture, there are few open source tools as well. One of them is Papyrus. However, you have to be a little careful in using those, because since it is an open source community, they are not very well maintained, and they can be a little difficult to get learning onto it. So it's a little bit, the learning curve is a little difficult, I would say, but it can get the task done. So that's one I can suggest for you to try it out.
Okay.
Yeah.
Thanks.
Sure.
There was a question in there about if we can use the drone example on the ConOps and the OpCons. I'll give it a go. So if you look at the drone example, so remember the two perspectives, right? One is from a stakeholder's perspective, the other is in the operational context. So from a stakeholder perspective, you can think of it as in the operational concept from the drone pilot's perspective, from the receiver perspective, from a regulatory perspective. For example, from a regulatory perspective, it might be what are the safety regulations that would be applicable that the drone would need to comply with. And so it's each of those perspectives bringing in what's relevant for that stakeholder. And in a concept of operations, it'll be the full, the life cycle of the drone, right? From the time setting it up, it'll be all of that, the get ready, get set, go, get unset, get unready, in its operational context, all the things that happen in that scenario.
And just to add to that, maybe if we have a multi-purpose drone, let's say, so the ConOps would vary from mission to mission, whether I'm delivering one package or two packages or what kind of package. Maybe I'm transferring medical supplies versus some other stuff. However, OpsCon could become by and large same if the overall operation is same, right? So that's a little difference I would like to add, but not always.
Yeah. Does anyone have any lessons learned from your own application or challenges that you currently face in your application of systems engineering in general, or specifically that you sort of learned and you think this is really important, or this is something I'm having trouble with?
Yeah, trying to explain to your bosses why it is helpful to invest money in NBSC. That's my biggest challenge right now, JB.
Yes, yeah, that is the I guess the all enabling challenge all the time, right? I mean, it's considered, why do I have to do this overhead when I can just go in and build a system, right? Why do you need all this stuff? And I think the it's becoming more and more obvious that this is needed because of the complexity of systems as we go forward. There's more connections, things are more interconnected, and things can go wrong. So the risk of things going wrong is rising. And one of the biggest challenges is the fact that a lot of this investment in engineering systems properly, if it's not safety critical, the justification becomes hard. And the other thing is that you only find out things are wrong as you get further into a project. And so a lot of the time people just bury their head in the sand and don't want to face the problem and just keep pushing it further and further out, right? So I think if you want to justify this, recently there've been a few, I know one PhD thesis that was done that was just on return of investment on systems engineering, and I'm trying to think of who it was. I think it was an Australian guy, Eric Honor, Honor,
Yeah,
and his thesis was on return on investment on systems engineering, which is a good reference if you're looking for examples. So they did case studies on large organizations that apply systems engineering and how they had shown the benefit of its application. Companies, big companies, I think Lockheed probably was one of them, and a few other sort of big companies in that space, where he managed to get in there and get some data from them. So that was one thing. What about the application of these systems concepts? Are you seeing examples as happened, for example, in the rats of Hanoi, where people were applying quick fixes and things, temporary things get okay, and then it all gets bad afterwards? Are there any things you're seeing in present day society that sort of reflect those sorts of quick fixes being applied that will come back and bite us in the future? Or are you seeing projects that are being worked on in that regard that will come back and bite? So there's a classic example today in Australia. There was an announcement made by government to cancel a $90 billion submarine project and to change to a different approach. And you probably hear about it in the news if you haven't heard already, which was a massive change, right? $90 billion complete submarine project has been canned, and now they're moving into a different way of doing it. I mean, there's lots of controversy about it too, but it just goes to show, how things, if you don't deal with the issues up front and you keep pushing them out, at some point they're going to break. And perhaps luckily this one broke sooner rather than later. But any things like that anyone's come across, your own experiences that you sort of knew something was going to go wrong, no one did anything, and then it sort of went wrong afterwards?
I don't know if it was going to go wrong, or if anyone anticipated it. But if you look at the first lockdown that happened, different parts of the world reacted differently to COVID situation, right?
Yes.
Let's say India and Australia, completely different approach, or US and Australia, completely different approach in different times. And it had the common underlying that almost everyone faced was the small businesses getting impacted, or the daily wage earners getting impacted. Some part of the world heavily impacted by that. And we are seeing a lot of sort of a cyclic wave in that. Like many workers who were working in the large cities, moving back to their smaller places, smaller towns, going back to their towns, and then a lot of jobs lost. And now suddenly, when everything opened up, there was a challenge of laborers coming back in, right? So you do not have enough resources or people to get the job done. And then again, the same lockdown happened. And so it's very, very much unanticipated, and nobody has the right answer that whether what was the right approach. So
yeah, and what happens is when no one has that answer or people don't have direction and scope, sadly there are two forces that prevail, right? And the two forces are fear and opportunity. So people do things because they're scared of stuff, and then there are people that take advantage of the fact that there is fear to benefit from it in a negative fashion. And I think I'm seeing that quite a bit, with this COVID situation in a number of scenarios. There's a lot of fear-driven stuff, and there's a lot of opportunities being had by people taking advantage of it. So yes.
Yeah.
Yeah, we have. I think we're almost at the end of the time too, but it's been good.
Right.
Yeah. Any last questions? Anyone else got any last sort of points you want to make, or general observations too? That's fine.
We've also shared a feedback form in the chat, so please do take time to fill it out. It's just less than a minute. We'll be happy to receive feedback.
All right. Thanks, JB. Thanks, Udit. I gotta go. Thank you very much for this wonderful presentation, and thank you everybody else. Thanks.
Yeah. Thank you for joining and
thanks, Barry.
part of this.
Thanks everyone as well.
Really appreciate. Yeah, we'll hang out for another few more minutes if anyone wants to catch up.
Thank you. Really enjoyed that. Thank you both.
Thank you.